Okay, class, today we're going to be covering section 3.2, part 1. So let me bring it down. Section 3.1 was linear. Section 3.2 is exponential, which is a lot how things grow and populate, like the coronavirus. This is kind of crazy that we're doing this right now. So exponential, we're going to go into the graph just a little bit on the next one, but an exponential graph goes like this. And so that's why when they're saying, do you hear on the news and stuff that we have to bend the curve? That's the exact curve that they're talking about. They want it to stop growing exponentially, because a linear graph, which was 3-1, right? A linear graph, I mean, even if it's here, you know, at some point, by the time this line gets here, okay, I can even still see it. By the time that this curve, it would be, oh, it's even off the page, there it is. It's so far up. Exponential growth is crazy. At the beginning, it hangs around with a line. And so you can't tell much difference. You're like, who really cares? But all of a sudden, once it starts taking off, there's no stopping it. And that's the concern. That's what they're saying. If we get, to the point of no return, then we're in trouble. So that's what they're talking about. And we'll talk about this one more time in the next section. We're going to look at the graph again. Or not in the next section, but in part 2. We'll kind of look at the graph a little bit more. But just so that you understand, exponential growth goes very quickly. At the beginning, not so much. But once it gets going, there's nothing in comparison with a line anymore. Okay, so this says an exponential, make sure I spell it right. An exponential function is a function that changes at a constant, not a constant, we don't want to use the word growth rate or anything like that, because that's more linear. So it's at a constant percentage rate. So kind of the nice thing is we're going to be able to kind of recognize these because there's going to be a percentage involved. So when we kind of see a percentage, we can associate it with an exponential. Okay. All right, this is just an example, kind of compare linear to exponential, just a little bit for us here. So I had a party, there were 6 people at the start of the party, 3 more people came each hour. Okay, that's linear. You're adding the same amount each time, that's linear. So we have, let's do hour 0. Okay, at the start of the party, there were 6 people. Okay, how many people were there after an hour? 3 more people came each hour. So we add another 3, now we've got 9 people. Hour 2, we've got another 3. We're just simply adding 3. That's linear. We simply add the same amount. So we got another 3, that's 12. Hour 3, what do we have? Another 3 people. So that is 15. Okay, let's do one more. Hour 4, another 3 people, that's 18. Okay, and we could actually write this. Y equals mx plus b. What's my growth rate here? What do we grow by each time? We grow by 3 people, right? 3 people. And b, what is the start of the problem? 6. There's my equation. Okay, but just visually kind of understand what's happening. Okay, let's take a look now at exponential. I had a party, there were 6 people there at the start of the party. Each hour the party grew by 50%. Okay, so at hour 0, we had 6 people. Okay, at hour 1, how many people did I have? Well, I have 6 plus 50% of 6. So I have to figure out 50%. Now, that you might even be able to do in your head. What is 50% of 6? That would be 3, right? So this is 3, so I'm just going to write it again. The 6 plus the 3, which is going to give me 9. Okay, hour 2. I have 9 people, okay, plus 50% of the 9. Okay, so 9 plus, Half of 9, that's a little bit harder. Half of 9 is what, 4.5? Okay, 13.5. Now, I know that you can't have decimal people, and that's maybe the negative about exponentials, but just to kind of see the growth, we could always round it, right? We could always round to 14. That would be okay, round to 13 either way. All right, or truncate. I guess you technically like say truncate to 13, round to 14. It's just a approximate anyways. This is approximate. 3 people, or hour 3. Let's start with the 13.5. Let's go with the most accurate number, even if we would round that, times 13.5. Okay, so 13.5, and then plus half of 13.5. Well, half of 13.5 is 6.75. So that gives us a total then of 20.25. Okay, and that's even, I mean, we could just round that to 20. That wouldn't be that big of a deal. Hour 4, 20.25 plus half of 20.25. Okay, I mean, that we could even do, right? Half of 20 is 10. All right, if we did the exact numbers, but if we just want to round this to 20, we could even do that. Again, if you're going to take it out further, then you don't want to round, but just kind of understanding things, we could round if we wanted to. But otherwise, it would be, what, 20.25 plus, and this would be, what, 10.125 for a total of right around 30 people. Okay, and so this also gives you a visual. Look, look at the beginning. 6, 9, 12, 6, 9, 13. Okay, if we rounded down, we would be at 13. See what I'm saying? At the beginning, very similar. But what happens? Hour 3, we get a little bit more, and already hour 4, we're moving. Okay, we're starting to increase, and you would see this would go up slowly, and this would start to increase. Because look at my percent. I'm taking now a percent of a larger and larger number each time, and that's where it starts to grow. Okay, now kind of some different things to look at this pattern too. Notice I have my initial value, and then I take half of it. I have my initial value, and then I take half of it. That is, and this half is the percent. Okay, so this half is the percent, because 50% is half, right, 0.5. That's what's down here. In general, we do initial value, okay, and then times 1 plus the rate to the x power. Okay, that would generate this same thing. In fact, let's do it for this 4th hour. So my initial value, this is kind of nice too. This formula allows us not to have to write everything out. So just like here, if I wanted the 20th hour, I could just plug a 20 in here and be done and get it right away. Same thing here. If I want the 20th hour here, I just plug it in right here and get it done. So this data goes with this equation. This data goes with this equation because it's exponential. So let's try the 4th. We know it's this guy. So y equals, what's my initial value? How many people did I start with? 6. Okay, 1 plus r. R is your percentage rate as a decimal. So 50%, I'm going to put in 0.5, okay, and then to the x power. So, can you guys see? Okay, yeah, I want to make sure you guys can see. Y equals 6. This we could add together, 1.5. And if I want to know what the 4th hour is, I would put a 4 in there. Okay, grab your calculator. Let's do 1.5 to the 4th, and then take it times 6, and you get this guy right here. Okay, so that, we know y equals mx plus b. For linear, exponential is initial value times 1 plus r to the x power. Okay, those two correlate to each other. This one's linear, this one's exponential. The only difference here is decay. If something is decreasing, then notice we subtract the r. Okay. All right. All right, so let's try. So now, we were so used to y equals mx plus b, now we got to get used to our new equation here. So hopefully we'll write it enough that we'll get familiar with it. Okay. Oh, also, let's talk about one other thing. Okay, so y is the end amount. Y is your end amount. R we said is your rate. And x almost always is time. All right, number of periods, usually time, minutes, hours, or days. So kind of keep that in mind. If you see time, that's your x. An actual value, that's your y. Like your end, I'm sorry, your end value, that's your y. Your initial value goes right there. Okay, R is your percent. R is your rate as a decimal. All right, so let's try some. Let's make sure you can see. Okay, U.S. healthcare expenditures. So the cost of healthcare in 2010, it only reached $2.47 trillion. All right, one prediction is that in the near term, they will grow by 6.5% each year. Assuming that this growth rate continues, find the formula that gives healthcare expenditures as a function of time. Okay. If this trend continues, what will the healthcare expenditures be in 2030? Okay, so for line, we're used to writing y equals mx plus b. For now, for when we see a percent, I'm trying to think, do they say anything about, as soon as we see a percent, then we're thinking exponential. And so we have to think y equals initial value. If it's increasing, it's going to be 1 plus r to the x. Okay, if it's decreasing, it's 1 minus r. So that's kind of like our new equation now. And I'll give you that on the test. I'll give you this. Well, you'll have it because it's open notes. What am I saying? Okay, so you can just use that. That's fine. Because you'll still have to identify that, hey, there's a percent, so I need to know that it is exponential. Okay, all right, so what is our initial value? Our initial value is how many dollars at the start of the problem. Now, we have to understand that this start of the problem is 2010. Anything past that, this equation doesn't hold true for. So 2010, 2.47. Technically trillion, but we'll just work with 2.47. 1 plus. Okay, now what is our rate? We just have to be careful. 6.5 is a percent. So how do we make it a decimal? We have to go 2 places to the left. So 0.065. And then x. That's it. Our equation is y equals 2.47, 1.065 to the x. Okay. You cannot multiply these two together because this one has an exponent. Order of operations says you have to do exponents first. So we just leave it like that. That's our equation. Now, can we use this equation? If the trend continues, what will the healthcare expenditures be in 2030? So that goes in for x. That's our time. Now, we don't put in 2030. We don't even put in 30. It's how many years is it since the start of the problem? How many years is it from 2010 to 2030? So we need to plug in 20. Okay, so from here to here is 20 years, right? From 2030 to 2010. You always have to acknowledge what is the start of your problem. Okay, that's where all the problems begin, right? All right, so 2.47, 1.065 to the 20th. Okay, and that's it. I got something like 8.7. This is money. And it's 8.7 trillion. Oh my goodness. Okay, try not to think about that one right now. All right, let's take a look at the next one. With new technologies and new types of successful business ventures, it is common for growth to be approximately exponential. An example is the growth in the number of internet domain hosts. One model is that the number of domain hosts grew by 43% each year. The number of domain hosts in 1995, so that's the start of our problem. Everything's based off in 1995, was 8.2 million. Find the exponential formula that gives the number of hosts in terms of time since 1995. So they even remind us everything's based off in 1995. What number of internet domain hosts does the formula give for 2005? Okay, so first we got to get our equation, right? So y equals initial value, 1, is it increasing or decreasing? Growth, so plus r to the x. Okay, that's our new formula. Initial value, everything starts at 1995, so 8.2. This time it's only 8.2 million. The rate is the percent. You just got to make it a decimal. So 43%. How do I make that a decimal? 1, 2. So 0.43 to the x. Okay. Y equals 8.2, 1.43 to the x. Okay, just leave it. Remember, don't multiply those two. You have to do exponents first. Okay, so that's our equation. Now it says what number of internet domains does the formula give for 2005? So we have to figure out how many years is it from 95 to 2005. Okay, that's not too bad. That is what? 10. So 8.2, 1.43. You have to, just because they give you the year, you have to figure out how many years that is from the beginning. Okay, and so beginning of the problem, which the problem was 95. So that is 10. Okay, make sure that you do, if your calculator does order of operations, you're okay. Otherwise, you have to do this first and then take it times 8.2. Okay, and so we should get something like 293.2, and then the units are million. Okay, because another way to check here, 95, it was 8.2 million. In 2005, it's 293 million. Oh, that's a pretty big increase, but that's the whole point. Once it starts going, it goes up quickly. All right, this one's kind of interesting. After antibiotics are administered, because we've all taken antibiotics unless we're allergic, right? But you know, that's a very common thing that we take, and we do have to consider, right? It decreases in our body as our body uses it up. So that's what the doctors decide how often we should take our next dosage. All right, after antibiotics are administered, the concentration in the bloodstream declines over time. Okay, that's going to be important too. Amoxicillin is a common antibiotic used to treat certain types of infections. Suppose that 70 milligrams of amoxicillin are injected and that the amount of the drug in the bloodstream declines by 49% each hour. Find an exponential formula that gives the amount of amoxicillin in the bloodstream as a function of time since the injection. Okay, and then how many milligrams of amoxicillin are in the bloodstream after 5 hours. Okay, so y equals I, 1. Now this is, it's declining, right? The body uses it up, and so the amoxicillin is decreasing. So this is going to be 1 minus r to the x. Okay, so the other one's talked about growth or increase. This one talks about decline, so it's going to be minus. Okay, initial, how much amoxicillin do we start out with? 70 milligrams. Okay. All right, what's our rate? Our rate is 49%. So we just have to make that a decimal, 2 places to the left, so 0.49x. So once we caught that negative, or that subtraction, it was a decline, then we're in good shape. Let's subtract that. We can subtract that. That gives us what? That should give us 0.51 to the x. Make sure you can still see it. Okay, slide it up a little bit. Okay, so how many milligrams of amoxicillin is in the bloodstream after 5 hours? This is great. We don't, time at the beginning was 0. So after 5 hours, we simply plug in 5. So y equals 70.51 to the 5th. Remember, don't multiply these two together. You have to do this first, 0.51 to the 5th, and then take it times 70. So that should give us 2.415. So at the beginning of the problem, we had 70 milligrams. So after 5 hours, we have about 2.4 milligrams. Good. Let's let's see, I was trying to think if there's anything else. Let's try another one of these guys. We're cruising. Oh, 20, okay. So 20 minutes. Let me do this. Okay, here we go. The balance of an investment is decreasing. Usually you don't want to hear an investment is decreasing. So just be aware that this problem, I mean, it does happen. So but the key word here for us is decreasing by 15% each year. If the original investment is $1,000, find an exponential formula that gives the balance B after T years. Then use the formula to figure out how much money the investment will have in 7 years. So if it's decreasing, and it stays that way consistently, which hopefully it won't, but if it stays that way consistently, we're definitely going to have less than $1,000 in 7 years. Okay, so y equals initial value, 1 decreasing, so minus r to the x. Okay, now just keep in mind in this, I don't know if you have to write the equation or whatever. Here, it doesn't matter for me or the test, but this wants balance, and then it wants it after t years. Okay, so it gives the balance in terms of time. Balance in terms of time. So that was that. This was just having us change the x and y values. Okay, so what's my initial value? I start out with $1,000. Okay. My rate, maybe we don't even have to rewrite it. My rate is, moving 2 places to the left, 0.15. Just remember you're subtracting because of the decreasing, and then to the t. All right, so what does that give us? 1,000.85 to the t. Okay, and then how much will it be after 7 years? Well, at the start of the problem, it was 0 years. So how much will there be after 7? So with this one, we just literally get to plug the 7 in. 1,000.85 to the 7th. Okay, and that should give us something like 320.58 cents. Okay, now at some point, if this continues very consistently by 15%, at some point we're going to reach negative money. So this was kind of in the last section too with the lines. Just keep in mind that this equation might not hold true for every time possible. Okay, at some point it might just not correlate to what's going on. I think that was happening with the very first problem in the last section. Something was declining, and at some point some of this decline, even if it's really close to 0, but definitely once it passes negative, it doesn't really pertain to money anymore. Okay, all right, but for right now, that's how much we have. Okay, let's take a little bit about half-life. Okay, this says, what is half-life? Okay, the long half-life of radioactive waste materials is one of the major concerns associated with the use of nuclear fuels for energy generation. Elements have different forms called isotopes. The isotope plutonium-239 has a half-life of 24,000 years. Suppose that we start with 100 grams of plutonium-239. Let's talk about what are we talking about with half-life. Okay, so we start out, this is years. We start out at 0 years. At 0 years, we have, was it grams? Yes, we have grams. We have 100 grams of this plutonium. Okay, 100 grams. Now, half-life means this is cut in half. Okay, so this goes down to 50. But how long does it take to get down to 50? The half-life is 24,000 years. So it takes 24,000 years to go down from 100 grams to 50 grams. Okay, now half of 50 is 25. We know that. How many years? It's another 24,000 years. So it's actually, what, 48,000? All right, 48,000 years to get down to the 25. Okay, all right. Another, if we cut that in half, we could do that, right? That's 12.5. Okay, how many years though? Another 24,000 years. So that's now 72,000. Okay. All right, so you get the idea. So it takes this many years to cut whatever we have left in half. Okay. All right. So this says, okay, so this is our formula for half-life. Amount remaining. Let me check one thing here. I'm wondering if I have, okay, so we're okay. All right, so I had a little bit different note sheet, but I think we'll be okay. All right, so amount remaining equals initial amount. How come this is 0.5? Because half-life is literally cuts it in half, so we can actually go all the way down to 0.5 right away. And then the only kind of different part, or we have to make a note of, is H is simply the number of half-lives. The number of half-lives. How many half-lives? Okay, so H is the number of half-lives. Okay, I think, okay, so we did that. Okay, all right, so let's try some. Your pages might be a little bit different. You might have an extra problem, which I did. I'll show it to you at the end, okay? All right, so let's take a look. Let's take a look at some of these half-lives. A certain radioactive substance has a half-life of 450 years. If there are initially 20 grams, find a formula for the exponential function that gives the amount remaining after H half-lives, and then how much remains after 720 years. Okay, so what's our formula for half-lives again? And you could just do Y, whatever you want. If you want to write amount remaining, that would be okay. It's initial amount. We could do, it's decreasing, so we could do 1 minus 0.5, but otherwise, basically, we can just go to 0.5 times H. Okay, but H is your number of half-lives. Okay, so what do we want to know? If there was initially 20 grams, this is easy, right? Our equation is 20.5 to the H. That's our equation. Now, this just gets a little bit trickier. What are we going to put in for H? H is the number of half-lives. We're talking about years. So we have to know in 720 years, how many half-lives were there? Well, every 450 is a half-life. So you're technically putting them into groups of 450. As soon as you're putting them into groups of 450, you want to divide. Okay? As soon as you're putting them into groups. Every 450 is 1 half-life. Okay, so we're not even going to hit 2. I think this is 1.6. Okay, which makes sense, right? Because what would two half-lives would have to be 900 years. Okay. All right, so then we plug that in. So that's the hard part. You just got to divide and come up with the number. Let's write this. This is the number of half-lives. And you can have a part, you know, because that means we're not quite at 2, right? So you can have a decimal there. So this is 0.5 to the 1.6. Okay. And that should give us something like 6.6. So how much is remaining? 6.6 grams. Okay. All right, let's take a look. Same thing here. Iodine 131 is a radioisotope with a very short half-life, 8.02 days, okay, which makes it very radioactive. We even use it in thyroid therapies. What does it say? It's one of the most feared isotopes released into the environment, okay? If you have 50 grams of iodine 131, how much remains after 35 days? Okay, so let's go y equals I, 0.5 to the H. Okay, so this is half-life. What's my initial amount? 50. Okay, that's not too bad. Okay, so the only thing we need to recognize that we're talking about half-life, so we go right to this formula. That's not bad. We just need the initial amount, and then remember H is the number of half-lives, So we've got 35 days, and we want to group them into 8.02 days. Okay, because every 8.02 is another half-life. So roughly 8 days, every 8 days is a half-life. So we want to know how many of those are in 35 days. So we simply divide that out. It's a long decimal. I went out 3 places because then after that it was like 0 and then 8. So it's kind of like a nice place to stop. It's up to you. The further you take it out, since we only have to do one thing with it, the further you take it out, the better. Okay. And then we just type that in. Make sure you do this first and then times 50. So I got 2.4 grams. Okay. Good. All right. I'm not sure, like I said, I have a little bit different note sheet. So let's just take a look at this one problem. For mine, it'll be what is written already, but that's okay. All right, let's take a look. If you don't have this problem, you're done. If you have this problem, then let's take a look at it real quick. This would be back on page 3. So let's take a look. It says, in many cases, removing dangerous chemicals from waste sites can be modeled using exponential decay. Okay, so if you're taking stuff away, you're trying to clean the water, you're taking stuff out of it. So that would be decay. This is a key reason why such cleanups can be dramatically expensive, because everything takes time, right? Suppose for a certain site there was initially 20 parts per million of a dangerous contaminant, and that our cleaning process only removes 5% of the remaining contaminant each day. Okay, so it's not going to remove everything. Every day it kind of removes 5%. Okay, maybe I can even cover this up. Let's see. How much contaminant in parts per million is removed during the first 5 days? Okay, so now this isn't half-life, so we're going back and forth, and that's okay. So let's do y equals initial and value. This will be good practice. 1, it is a decay, so it's minus r, and then to the x or to the t for time, but we can just do that. Okay, so are we okay? It's negative because we're removing stuff. So y equals, what's our initial amount? Our initial amount is, I guess we could do it like this. Our initial amount is the 20, okay? And then it's 1 minus our 5%. So I changed it to a decimal, 0.05 to the x. Okay, so then I just subtracted those. That gives me 95. This is kind of a key part here, and this is right. It's not like we were doing anything wrong, but if 5% is being removed, what percent remains? 95% remains. So I am finding how much remains, how much is still in the water, how much is left. I don't know if you can read that. So that's what's happening here. Maybe I'll just retrace it to make sure that you guys can see it. I don't know if you can see the pencil or not. Okay. So we said this is y equals, this is 20.95 to the x. Okay. But then the key says, this says how much remains or how much is left. So we just have to remember our formula isn't wrong, but we just have to remember our formula is telling us how much is left. Okay, so then it says, so that's it. How much contaminant, here's the problem. This question, if it's on the homework, says how much is removed during the first 5 days. So I said, okay, well, I got this equation. Why don't I just plug in a 5? So I plugged in, so there's 20.95 to the 5th. Okay, I plugged in my 5, and I got my answer. But this is how much, let me write it. This is how much is left, okay? This is how much is left. This is how much remains. I want how much was removed. So I have to do 20, because that's how much I started with, right? 20 is how much I started with, and then I have to subtract my 15.48. So this one's a little bit harder. Just remember that the equation that you write gives you how much remains. If they're talking about how much was taken away, then you have to do this extra piece at the end. Okay, that gives us 4.52. All right. Good luck, guys.